Now we can calculate the various perturbation terms. We're going to start with our first order equation here, and we're going to pre-multiply by psi m. Remember, we had decided that we were going to look at perturbations to this specific state, psi m. So doing so, on the left-hand side here, multiplying by psi m on the left-hand side of this equation, we can associate, if we like, with this parenthesis. Now, here we come across one of the very convenient things about the Dirac notation. It's perfectly meaningful to consider h0 operating to the left, or if you like, this entire operator h0 minus em times the identity operator. But this operating on the left just gives us em times that wave function. So, as a result of working on this left-hand side here, we can rewrite that as follows. And of course, that's just 0 because we've got em minus em in the middle. Now let's look at what happens as a result of this pre-multiplication on the right-hand side of the equation. Well, in that case, we've got psi m times e1 minus the perturbing Hamiltonian times psi m. Well, psi m e1 psi m is just e1 times psi m, which of course psi m gives us 1. So that's just e1. And then we've got minus psi m hp psi m. So that's this here. In other words, equating this to 0 and moving things around, we have e1 is equal to psi m hp psi m. A very simple result. The first order correction to the energy is just the matrix element of the perturbing Hamiltonian for psi m and psi m. And that's our formula for the first order energy correction E1 as a result of this perturbation HP. We can go on to calculate the first order correction to the wave function phi1. What we're going to do is expand that correction, this phi1, in the eigenfunctions of the unperturbed problem, psi n. So this is the whole set here. Well, of course, it's straightforward to write that down. We'll get some set of coefficients, which we call an1, multiplying each of the psi n. And we substitute this back into our equation here. So we're going to substitute that expansion in here. And we're going to pre-multiply by psi I. On the left-hand side, that will give us psi I times h0 minus em phi 1. Well, h0 operating on psi I is just ei, and the psi I. So that becomes ei minus em in the middle here. We can take that out as a number, and we're left with psi I phi 1 with this number out in front. But of course, this is just ai1. So we're left with this result here. So that's what happened multiplying with psi I on the left-hand side of this part of the equation. And now we can deal with the right-hand side. So pre-multiplying the right-hand side by psi I gives us this here. And of course, we can take the e1 out. That leaves us with e1 psi I psi m. So that's this. Minus psi I hp psi m, this term here. So with that expression we've just derived, equating the two sides that we came up with in our equation, we're now going to presume that the energy value Em, the unperturbed energy value, is not degenerate. That is, there's only one eigenfunction for this eigenvalue. With no degeneracy, we still need to distinguish two cases here. First of all, if I is not equal to m, from this equation that we have here, since we're not looking at a degenerate case, ei is not equal to em. And so we can rewrite this equation right away, dividing on the right-hand side by ei minus em. So now we have an explicit formula for this expansion coefficient. But on the other hand, if I is equal to m, then going back up to our equation here, obviously, with I equal to m, this is 0. And if we look at the right-hand side here, if I is equal to m, then psi I, psi m is just 1, so we've got our first order energy correction here, and we have this expression, I equal to m up here. But that is just our expression for E1, so we've also got 0. So we've got 0 equals 0. Well, what's the point of that? The point of that is that we have no constraints on what we choose for AM1. Our algebra here does not tell us what AM1 should be. Now that might seem like bad news, but it turns out that it's actually quite good news. We are therefore free to choose this to be anything that is convenient. The choice that makes our algebra simplest is simply to choose to set up our algebra taking this coefficient to be 0. You might think we're doing something in the physics here, but we're really not. We would just be adding in part of the original unperturbed wave function. That really has no physical significance to it. We would end up having to rescale all our algebras as a result. So it's simpler just to choose this equal to 0. We could construct theories with it not equal to 0, but there would be no benefit to it. And there's no need for us to choose it to be anything other than 0. So that's the same as saying that we choose to make the perturbation to the wave function orthogonal to the original unperturbed wave function. That's what we're choosing. There's really no physics to choosing to put a part in here that is not orthogonal to that. We would construct a self-consistent theory, but there's no point in doing it. It would give the same answers in the end, but there's no point in doing this. Now, incidentally, if we look at the higher order equations, we will get exactly the same phenomenon occurring, and we won't go through that algebra explicitly here, but the same thing happens. So quite generally, what we're going to do in our perturbation theory is to make the overall convenient choice that all of the perturbations to any order are each orthogonal to the unperturbed wave function. We're always free to make that choice, and it makes our algebra much more convenient. So, hence, with our expansion coefficients now worked out, we have this explicit formula for any given expansion coefficient except for I equals m, and for the case of the expansion coefficient of the original unperturbed wave function here, we're choosing that to be 0. So the first order correction to the wave function is given by this expression. Here are our expansion coefficients multiplying these original basis functions here. The summation is over all n's except n equal to m. We are explicitly excluding that. That's because of this statement here. And we have the first order correction already to the energy, and so these are the results of first order perturbation theory. Therefore, to the extent that the change of the system as a result of the perturbation is linear in the strength of the perturbation, we figured out what both the changes in the wave function should be and what the changes in the energy should be. We can continue similarly to find the higher order terms. So we take our second order equation and we pre-multiply on both sides by psi m. So on the left-hand side, we have psi m times all of this. That's all of this here. Of course, h0 operating on psi m is just em psi m. So we've got this number in the middle here, which of course is 0. So the left-hand side, as a result of this pre-multiplication by psi m, just gives 0. And then on the right-hand side, pre-multiplying by psi m, we have psi m times this here. This is a number, of course. And psi m e2 psi m. Well, this here, the E1 with these two terms here, is E1 psi m phi 1. We have minus psi m HP phi 1. That's this term. And of course, psi m E2 psi m, well, psi m is just 1 and E2 is just a number. So this is E2. So E2 is equal to psi m HP phi 1. That's taking this term over to the other side. 0 here, so we take that over to the other side. And we have this term also taken over to the other side. But we chose phi j to be orthogonal to psi m. We said that we would always find that in our algebra if we followed it through, that we could make that choice. And so, therefore, we're just left with these terms, that E2 is equal to psi m hp phi 1. So you see, incidentally, that the second order energy correction depends upon the first order correction to the wave function. If we use the result for our first order wave function correction that we already figured out, which was this expression here, we can put that back in here if we want and obtain a more explicit expression for E2. But of course, we can take this if we want inside the expression here. Note that it's psi m hp. This is just a number, so that's all really operating on psi n. So equivalently, therefore, we end up with the modulus squared of this matrix element here. That is, we've got psi m hp psi n times psi n hp psi m. This is the complex conjugate of psi m hp psi n, and so we have the modulus squared here. So we have an explicit expression for the second order correction to the energy. Note incidentally that it's proportional to the square of the magnitude of the perturbation, which makes some sense. For the second order wave function correction, we expand phi 2, noting that phi 2 is chosen orthogonal to psi m. So phi 2 is some coefficients, an2 times psi n. And again, we are choosing n not equal to m. We're not going through that algebra explicitly, but we would always find that we could choose phi 2 to be orthogonal to the specific unperturbed function psi m. Now we're going to pre-multiply our second order equation on both sides by psi I to obtain on the left psi I h naught minus em phi 2. Well, of course, h naught operating on psi I here just gives us ei. So again, this turns into ei minus em, and psi I phi 2 by definition is ai2. Pre-multiplying on the right-hand side by psi I, so we put psi I in front of each of these two terms. Well, for the first one here, and the E1 part, we have psi I E1 phi 1. Well, that is E1 times psi I phi 1. And that is just E1 AI1, because psi I phi 1 is AI1. For this psi I HP phi 1 with a minus sign in front of it, well, we can fold the psi I HP inside the expansion for phi 1. So that's what we've done here. We have our minus sign because we had our minus sign. For this term here, by definition, we're only working out coefficients where psi I is not the same as psi m, where I is not the same as m. And that means that this term always vanishes by choice, because we're never dealing with psi m, psi m. It's back to this original choice that phi 2 is going to be orthogonal to psi m, and similarly phi 1 is orthogonal to psi m. So we're never going to ask for the coefficient where we chose to pre-multiply by psi m. So therefore, this term vanishes since that's just a number. So we're left with just these two terms. So finally then we have, from the left, this term here, from the right, all of these terms. Note the summation, as before, excludes the term n equal to m, because we chose this orthogonality. Hence, for I not equal to m, we have this expression here. So I not equal to m, so that this is not 0. We take this over to the right-hand side. So this term here is from this one. And we've flipped around the signs, incidentally, with ei minus em here. We've got em minus ei there, so that's why that minus sign is gone. And it's why we have a minus sign in this term here. So we get em minus ei here, where we had ei minus em up here. Note, incidentally, that the second order wave function correction depends only on the first order energy and wave function. So these an1s and the ai1 are coefficients that we get from the first order wave function correction. So let's summarize our first and second order perturbation results. For first order, we have that the energy correction is given by this expression, and the wave function correction is given by this one, where our expansion coefficients AI1 are as follows, with the exception that AM1 is chosen equal to 0. And in second order, we have this simple expression for the second order correction, where we have the first order wave function correction in here. And for the second order wave function correction, we have it, of course, as an expansion on our basis set here, where these coefficients are as follows, where again we've chosen AM2 equal to 0. So these are the results of first and second order perturbation theory, and these are the only formulae you need in order to use it.